Let's see, everybody can hear me okay? Ashley, you can hear me?
Mhm.
Okay, great. Hi, everybody. My name is David Millard. I am a second year, almost third year PhD student in the Robotics Embedded Systems Lab at USC. So I work on robotics research, mostly dealing with physics and control and sort of how can we control robots to be better in physics, physics difficult environments. So let's see, before coming to USC, I worked at Google X, which is the research and development arm of Google. I worked in a robotics group there for 4 years, where I mostly worked on navigation software to make robots navigate more safely in unstructured environments. And when I say unstructured, I mean like your house or your school, where there could be like desks anywhere, or you could maybe leave your clothes on the floor, rather than roadways, which are generally considered more structured because there's like a road and signs everywhere that tell you where to go. So I worked on navigation in unstructured environments. Currently, I am doing an internship at a research group, at Google that also deals with robotics, which deals with machine learning. So how can robots learn to control themselves better? I'm actually currently in New York City, even though normally I live in Los Angeles as a student at USC. And what else? Am funded by NASA, and the next thing that I'll do is work for NASA. I'm what's called a NASA Space Technology Research Fellow. So I will work on a tiny robot called Astrobee. I should put a picture of Astrobee in here, but it's like a 1 foot by 1 foot by 1 foot cube that flies around the International Space Station. And I'm gonna work on making Astrobee work more intelligently with objects on the International Space Station around humans. Yep, okay. So I wanted to talk to you today about something that I've gotten into for research, which is virtual worlds for robots. Oh, and before I start, Ashley and I discussed before, I can't actually see the chat right now, but if you have any questions for me or you want me to explain something or any question at all, just type it in the chat, and then Ashley can just interrupt me and read it. And please don't feel like you have to save any questions for the end. I'm happy to answer questions as we go. Okay. So today I want to talk to you about virtual worlds for robots. Why is that interesting? Like, what does a virtual world mean? There's a lot of things that could mean. And how can we construct virtual worlds, and how can we use them in robotics learning and training and programming. So robotics, the core of like a virtual world, when I say a virtual world, really what I mean is a simulator. So objects in the world always move according to the laws of physics. So like if you drop an object, it's going to fall to the ground, and this we call the law of gravity. But if you tie a string to the object and you attach the string somewhere and then you drop the object, well, if you look at this video, you see we get a pendulum. And so different laws of physics interact to create different equations of motion. So you can always write down some sort of math to describe how is a system going to change over time. And this will tell you things like the different forces that are involved, different distances, different speeds, velocities, positions of objects as they interact. And so if you look, there's a pendulum swinging, right? It looks kind of like a grandfather clock. And here we've drawn sort of a simplified model of this pendulum system, right? So we say there's a mass, which is like of mass M. There's a string of length L. We can say this, that the angle from the pendulum to straight down is called theta. So there's all sorts of ways that we can describe our system. And then once we've written down some of these characteristics of the system, we can say, okay, I know how the pendulum is going to move. I can tell you the speed if you tell me the position, or there are different things that we can say. And what this is called building a mathematical model and describing the equations of motion. what a simulator does is it enacts these same laws on computers. So you could imagine we could write a computer program that would describe the motion of a pendulum as it swings back and forth. So I could give you a different L, I could give a different L to the computer program and it would make a longer pendulum or a shorter pendulum, or a different mass, or I could describe different possible systems. But what's important is that the computer program can tell me how is a system going to change with time. And there's different equations of motion for different types of systems. So the laws of physics are very complicated in general. And so it's always sort of difficult to say, well, maybe a robot, because all of the parts of a robot could be rigid. Like if you think of a robotic arm, every link in this arm is going to be very hard. This is what we would call like rigid objects. And these perform, or they evolve according to certain specific rules for rigid objects. But maybe your pillow, if you bend your pillow, well, suddenly it's not a rigid object anymore. So we need to describe how springy your pillow is or how bendy your pillow is. And so there's different equations for what are called deformable objects. You can imagine fluids change in different ways too. So like the air around you is considered a fluid, or water as it splashes is considered a fluid. And these all have different equations of motion. But the unifying idea is that we want to write a computer program which sort of replicates this physics. So it builds a virtual world where the laws of physics are the same as the physics that we have in the real world. And simulators are really all around us. So simulators come up often. I think the most prominent example of physics that we see is in computer graphics. So graphics come up in video games, but they also come up in animated movies. So animated movies, specifically Pixar, uses a lot of physical simulation. And one of the best examples that I can think of very complicated and very cool physical simulation is the hair in the movie Brave. So if you look at the top right here, where you see the main character of Brave climbing up, you can see how her hair bounces around and it blows in the wind, and it's really complicated. I mean, it looks like a bunch of slinkies that are like sort of put together. I mean, her hair really looks like real hair. And the way that this is done is not by animators drawing or sort of describing each frame by hand. At Pixar, they have physical simulation teams that write physics simulators, and some of these simulators are for hair. So each hair is sort of modeled as a spring. It is really like a little slinky. And then the laws of physics for a spring are written down. And when the character climbs up, and when there's a force that moves her head, or when she moves her own head, or if there's wind, then the whole system of hair will actually react. So this is all computed through a physical simulator. If you look on the top left, then there's fluid simulation. So the water in the movie Moana it's simulated with a fluid simulator. And you can also see that her hair, especially when she stomps her foot at the end of this animation, her hair bounces, and that's also computed through a physics simulation. So hair animation, water animation, a lot of the physics that you see in animated movies is computed with a physics simulator. And then I have two more examples at the bottom. There's a company called NVIDIA, but they are also working on physics simulation for graphics. And so you can see these are very fast methods to compute, like what would cereal in a bowl look like if you had no gravity? Or like, how can we simulate hundreds and thousands of tiny objects all falling on each other? And so these are some difficult problems in simulation, but really what we're going for in graphic simulation is for something that looks right. So the main focus here is that we know kind of what hair should look like. We know what fluid should look like, and we know if I were to pour sand or pour a bunch of almonds or something onto a table, I know how these would collapse. And we want something that looks to our brains like, okay, yeah, that looks pretty right. Because really in our brains, we have a good understanding of physics and how it works. Even if we can't write down the equation, we know if something looks wrong, right? So yeah, so this is used in animated movies, it's used in movie special effects, it's used in video games, and in virtual reality. So it's important to know that this is really not the same thing as rendering. So rendering is what a system looks like. So when we see like that her hair is red and we see how the sun reflects off of her hair, or if we see like the color of the water here is blue, these are all parts of like a rendering pipeline. And that's actually very different from the physics. The physics is just how does the object involved change, and then we can decide how we want to show that object later. So graphic sim, I think, is probably the most visible view of physics simulation that people really see on a day-to-day. More related to robotics is engineering simulation. So in engineering, you don't want to have to like build an engine every time you want to test a different component of an engine. So if I say, maybe I want to make a cylinder a little bit larger in an engine, I don't want to have to build an entirely new engine and drill out a new engine block just so that I can test what happens if this simulator, or what happens if this cylinder size gets changed. So instead, what people do is they build simulators. And so you can see on the bottom left here, there's like a simulated engine, which will, like if I were to make one of the lengths a little bit longer to move some pieces around, really the simulator should behave like a real engine, like a real engine would work in the real world. You can see other examples here. So on the top, you could see it's a lot of fluid simulation is actually used to determine like what forces get applied to windmill blades. You can see on the top right that there's like a brake caliper, right? And you can see it changing color. So they're using color here to represent the heat of a brake simulator, or sorry, of a brake pad. And it's really important to know like how hot do brakes in cars get. And so one of the ways that people experiment with these sorts of things is by building simulators. So a temperature simulator based on how much friction gets applied to the brake. And then the bottom right, I was pulling these animations from a video, and they had a video of somebody writing down math, and I thought it was kind of funny because that's looks like a lot like what I do. Okay, so engineering. Oh, yes.
Before you go on, we have a question.
Oh, perfect.
Does CADing software have simulator built in?
Yeah, that's a great question. So CAD software is used for design. For people who maybe don't know that term, it's computer-aided design. Some CAD software will have simulators built in. I know there was a product called like Inventor, and I remember that was pretty famous for having some simulation built in. Generally, the CAD software is used for design, and then you can take the mechanism that you've designed and simulate it in some sort of other physical simulator. Maybe they're sort of integrated together, but really they sort of serve different purposes, even if maybe they are in the same like software package. But that's a great question. So CAD software is very related to design. Now, one thing that's actually very interesting is that we can use simulators to inform what a good design is. So some CAD software has packages to model what stresses and strains would get applied. So you can say, if I apply a force to this bracket, how does this force get propagated, or where does the strain happen across this material? And areas of low strain you can sort of automatically remove from a mechanism that you're designing. And it's a really good idea. It's a really important idea, is that there is actually a simulator that will tell you what strain gets applied at different parts of a mechanism. So yeah, I think that's an excellent question. Thank you for asking the question. Yeah, okay, so engineering simulators, they test for temperature, strain, pressure, forces, and really what we're interested here is not that it looks right. I mean, it's going to look right, but if it just looks right, that's really not enough. We really need it to behave properly, and we as engineers need to be able to see with our eyes, you know, can I interpret the output of this simulator, right? If the hair in Brave, if I can't understand it, but I know that it looks right, that's fine. But if I don't understand, say, a brake pad that I'm putting into a car, that's not so great. So we need interpretability and correctness when we have engineering simulation. And because we're so focused on correctness, these are often quite slow. So a lot of the methods used in engineering simulators are pretty slow. Great. So how does this apply to robotics? What is robotics? What are we doing? So we want to build robots. I want to build robots to perform difficult tasks. So there's tasks like space exploration, assisting humans. So if you have somebody who's sick or maybe can't help themselves in their own home, it would be great to have, if they don't have somebody who can take care of them, maybe you could have a robot that could help take care of them. Disaster relief. So if there's really dangerous areas, maybe there was like an earthquake or some natural disaster, and it's not safe for humans to go in, you need to have the ability to have robots go in and try to help people. Or there's all sorts of uses for robotics where, and the thing that's common about all of these things is that robots need to have an understanding of physics, right? So for disaster relief, maybe there's a building that's collapsed and there's pieces of rubble everywhere. Well, it's important to be able to reason about, if I move this block of rubble, will there be a bigger collapse? Like, will there be like will this cause some sort of landslide? Or for human assistance, you need to predict how a human's gonna move, but you also maybe need to make sure that you don't knock something over in a human's house. You need to understand how objects move. So for pretty much every part of robotics really need to understand the laws of physics. And I'm being kind of vague here, right? So like robot understand, like a robot, it's not a human. I mean, we tend to humanize robots, so we need to be really specific about what we mean by a robot should understand. But basically, whatever program is controlling the robot, it needs to account somehow for the laws of physics. There needs to be an embedding of the laws of physics, and the program needs to predict how the world is going to change. And the way that the world changes is what we call the laws of physics. And also, humans need to know that robots are going to be safe and reliable. So I mentioned earlier, I work on a project called AstroBee, which is a little robot on board the International Space Station. It's really important in space that everything is predictable, right? Because if AstroBee were to hit the wrong button, or were to go through some cabling, or were to hit something so hard that it broke something aboard the International Space Station, that could be really expensive, that could be really dangerous. All of these things need to be minimized. And so this is all about engineers, again, being able to predict how the things that we build are going to behave.
Another question.
Awesome.
Do you think the field of robotics will be more useful practically during this coronavirus pandemic?
Ooh, great question. Do I think it will be more useful currently? So I think to answer the question, I think that things like global pandemics, I think it might awaken in some people the idea of using robots. So I don't know if like currently robotics is really at the stage where it could be useful right now. Like we don't have like a secret bank of fully functional robots that can go into the world and just help people out right now. And I wish that we did. But I think what something like this global pandemic would do is always put in the mind of people like, okay, well, if there is a situation where it's no longer safe for humans to be here, maybe we do need to build capable robots. Like, and so I think things like this current world situation build an awareness of when robots can be really useful for society. Thank you for your question. I think that's an excellent question. Okay, so how do simulators get used in robotics, right? So this is virtual worlds for robotics. Now I think we're really getting to the meat of the issue here. So one way that we use virtual worlds, aka simulators, in robotics is for testing, right? So I have like a little analogy here. If you look at this picture and you look very closely at the picture, well, you don't have to look that closely. This is a surgeon or a surgical student who's wearing a headset. He's wearing a VR headset. So he has some goggles on that will show him a virtual scene. But what we're looking at is a rendering of the world that he's in. So if you look really closely, like the glove that's on his hand is actually like not a real glove. You can see like the wrist of his glove doesn't match up. So that's like a virtual glove. And he's working on a virtual patient. So this knee is actually a simulated rendered knee. So if I were a surgeon, and I'm not, and I had just learned how to perform knee surgery, I would really want to make sure that I knew how to do knee surgery really well before I actually operated on a patient. And so one of the ways that people are currently, and it's a new technique, one of the ways that people are practicing their skills for surgery is with virtual reality. So you can see he's holding some sort of device here. He's operating on somebody's knee. But if you can practice in virtual reality, and this is probably a fancy virtual reality setup where there's like some force that gets applied backwards so that if he hits the knee, it will give him some force backwards into his hand. But now he can practice, or she can practice. This is a male surgeon, but it could also be a female surgeon. The surgeon could practice their surgical skills, and this is fantastic, right? So we use the same kind of idea in robotics. So we can test any of our robotics algorithms in a simulator first. And so this is the idea where we have made a robotic algorithm that says, I'm going to fly around the International Space Station, or I'm going to pick up a book, or I'm going to do something. And we build a simulator of the International Space Station, or of a table with a book. And we let a virtual robot controlled by the same algorithm test out their skills. So pick it up or do anything that we want. And the benefits of this are a lot. So first of all, it's safer. So if we have an algorithm that doesn't work, then it could break something in the real world, right? And that's very unsafe. Also, when we're developing something, if the robot drops the book every single time it picks it up, then the engineer or whoever's developing the robot has to go over and pick up the book and reset it. Whereas in a simulator, you can just say, okay, you know what, put the book back on the table. It's all in the computer really fast. And it's cheaper. I think that the cost here is actually a huge thing for enabling many people to develop robotics algorithms. So you can develop robotics algorithms without owning a robot. Robots can be really expensive. Certainly not everybody can afford them. And I mean, I can't afford the robots that I work on unless I have access to them. So having a simulator is a great way for anybody to start to understand robotics. Yeah, and so my other point is that humans do this too. So pilots learn how to fly in flight simulators. Stock traders, if they're testing a new stock strategy and they don't want to lose a lot of money, they will work on a simulated stock market instead of a real stock market and see how it works. Okay. The other thing, and this is picked up a lot in recent years, is that there are now algorithms so that robots can learn. So you can learn from scratch, so robots can basically teach themselves by interacting with the world. And what we do as engineers is we say we only really need to tell the robot, have you succeeded or have you failed? And then the robot can try out different things, and they can see what works and what doesn't, and eventually the robot learns a successful way to perform a task. I want to be clear that what I just described, I left a lot of stuff out. So this can be pretty confusing, and it's a brand new field of research, and I think it's really exciting, and I think it would be great if anybody on this call was inspired by that to keep working on it. But this is a brand new field of research. But why do we want to do this in a simulator, right? So I have an example here, and on the left, you can see there's a robot where it hasn't learned very much. I think this is like maybe the 5th time it's ever tried to park in a space. We're trying to park in the red space. And you can see the blue car, it just crashes right into the truck, right? So this is super unsafe, but in a simulator, it doesn't matter. It's just a simulated truck. On the right, I think this is like 20 or 50,000 times that the robots practice the skill. You can see, okay, it goes right in, it doesn't crash into anything. So robots learning inside of simulators, it's much safer for failures. It allows robots to learn from scratch without destroying everything. You certainly don't want to park your car outside and then have somebody practice their robot algorithm if your car's parked in that parking lot. And sometimes this can be easier than actually programming the skill. So there's a lot of stuff to keep in mind if we're programming a skill, whereas if we just say, hey, you've succeeded or failed, a lot of times that can be a much easier question to answer. And you put a lot of the emphasis on letting the robot learn. The downsides to this can be really computationally intensive, and also simulators aren't 100% accurate. So if the robot says turn left in the simulator, maybe they'll turn left 5 degrees. In the real world, that same turn left for a robot may only be 4 degrees. And so you could imagine if the robot thinks, if it's learned something perfectly in the simulator and it tries to do the exact same thing in the real world, that's not exactly going to be accurate, and it could be really unsafe. So there's an exciting area of research about trying to match simulators to the real world, or trying to learn in a way in a simulator, even if it's wrong. How can I learn better in the real world? Okay, so now we're in my research area. I think this is my last slide, so I will take questions in just a second. But the exciting part of this all to me is that we can sort of combine the two things. So we can have robots that use simulators. They can use an understanding, a pre-baked human-coded understanding of physics to learn much faster in the real world. And so if a simulator is almost correct, then the robot only needs to learn the differences. So if we can simulate, for instance, here, this is work that's actually done by a researcher in my group at Google that I'm working at right now. If the simulator is almost correct, the robot only needs to learn very small differences between the simulator and the real world. So maybe when the robot releases the banana, there's like a little bit of extra friction. The robot really only needs to learn about that friction. It doesn't need to learn all about how to move itself. It doesn't need to learn all about like the arcs that objects form. It doesn't need to learn about how objects bounce if the simulator can account for all of that. And I think that this has a lot of benefits. So it's faster for robots to learn. It's easier for humans to interpret because we already understand a lot of how physics work. And it's easier to constrain these systems for safety because we have a good idea of how to model systems in physics. And it makes a learned system much easier to constrain. So this is what my research is on, and I think that this is sort of the most exciting route forward. So yeah, I want to say thank you for tuning in, and I really appreciate the questions that I've gotten so far, and if anybody has any more questions, I'm happy to take them.
Thank you, David. If there are no questions, maybe we can let Matt go ahead, and then at the end, if there are any questions for both of you, then we can start a Q&A.
Yep, fantastic.
Okay, Matt, whenever you're ready.
Great, okay, here I am. I'm just gonna kind of get set up here. If anybody wants to shout out a question for David, go ahead.
Yeah, there's one. Is there a research paper about the slide you showed last?
Yes, that if you look up, it's called TossingBot, TossingBot. That is the paper that describes that system.
Thanks.
For David before we transition over.
Cool. Take it away, Matt.
Awesome. Sweet. Well, it was good to see at least one person over video, so there's a little bit of evidence that like there are live human beings out there. This is kind of a crazy situation. Yeah, there we go. Now you don't all have to turn on your video. I'm sorry I missed the first part of your presentation, David. It looked really cool. I'm going to be talking about a study that I've been working on for the past year or so that involves an online game that we've been using to learn about human-robot interaction. So my work is going to be a lot more focused on how humans think about robots and how we can use like how studying that can help us make robots that interact better with people, work together better with people. I just wanted to throw up I'll just throw up a slide or two here, kind of as a visual aid. And then I want to show you some parts of the game. And we can kind of like pretend we're playing here for a moment. Share my screen. Okay, cool. Turn this on. Okay, so this is all of us. I actually did this work starting last summer, and most of the game that I'm going to show you was actually made by the two gentlemen in the middle who were visiting undergraduate researchers from Ohio State and from Berkeley. I forget which is which, but either Eitan or Matthew, one was a freshman. I think Matthew was a freshman and Eitan was a sophomore. So they were really early on in their college careers, and they did some really great work here. So you'll be able to see like how someone could just dive right into human-robot interaction research if you're at all interested in this sort of stuff. So kind of the point of this research is to, again, think about how people think about robots. So in this figure, there's, you've got a person looking at a brand new shiny robot. This is the Curie robot, which we have a couple of in the lab. Really neat robot. The little eyes can open and close. It can make little cute sounds and drive around. I think it was originally meant to kind of be like kind of a social companion, like it would take pictures of you and post them. I think it could post them on social media, which is a little bit weird. That company went out of business not too long after it started up. But the robots were great for research. They had a lot of really neat sensors on them. This one has like a laser sensor, a camera in one of the eyes. The head can move all around, so it can do all kinds of like expressive social motions. And it's just kind of shiny and cute. If you touch the head, it like closes its eyes and purrs like a cat and kind of like, ah, yeah. Like, so it's kind of pet-like, right? So we like it in the lab, and it's a good research platform. So when you first meet a robot like this and you're watching it kind of do its thing, psychologically on the inside, you're also, without realizing it, you're forming a lot of conclusions about the robot and what it can do. The stuff I was most interested in, because my previous research was about privacy, people's privacy concerns about robots, was how you figure out whether the robot can see, hear, record video, whether it has access to the internet, these sort of privacy relevant things, like what it can sense, what data it can collect, whether it could potentially send that data somewhere. That's what I did my PhD on before coming to USC. I'm a postdoc in the interaction lab. So I'm coming here right after my PhD to continue doing some research. So I'd done some experiments on privacy and found that I think a big gap in our understanding is like, how do people kind of come to believe what sorts of data the robot can collect without being told? Like, if you look at this robot, it doesn't have an obvious camera hanging off of it. It's not like holding out a microphone, like please speak clearly and loudly into the microphone. But when you hang around it, you kind of get a sense of what it can do. Maybe some things are still question marks, like you're not sure if it can hear, but you at least can probably tell that it can see something, or you think it can. But it's all just based on kind of implicit impressions you get from looking at the robot. But this is all like, this is all still like very new stuff. Science is very young in this area. Those were just kind of my intuitions. So there's a lot of research to be done. So this is what some researchers will call part of your mental model, which is kind of like your understanding in your head of the robot. So your mental model of the robot, in particular of the robot's perceptual capabilities, which is just what it can sense, what kind of data it can collect. So the point of this project was actually to go one step further and help the robot try to estimate what sort of beliefs the human has about the robot. Let me say that one more time. Help the robot try to estimate what sorts of beliefs the human has about the robot. Okay, so that's like pretty meta here. I'm going to switch over to start showing you the game. I should have just shared my screen altogether. Let's see. So this is a game we made. It's just a game in a web browser. So it's kind of a hybrid game where you're not like standing in the same room as the Curie robot, whom we call Denise in this game. But this actually works out really well for the current situation with the stay-at-home order, because we can't bring you to hang out with the robot, but we can have we can record videos of the robot doing stuff and have you still kind of sort of interact with the robot. So here's kind of how it works. Oh, first you do a survey. Let's see, do I have to fill in all these boxes? I think just age and gender. Spoiler alert, I'm old. Okay, here we go. I have neutral opinions about everything. Great, so the way we frame the game is as a robot Olympics game, which doesn't work well with the current stay-at-home order because the Olympics got canceled, but we're not going to talk about that. So blah, blah, blah. The important part is that the robot has some capabilities that it is aware of. So the robot knows what it can do, but you don't know what the robot can do. And so the point of the game is to try to work together with the robot when you don't know what it can do. And the robot is going to be trying to like work with that as best it can. This is not my first time playing the game. Cool. So it's kind of an abstract game where the robot's supposed to do these different tasks. So these are like events in the Olympics, right? But they're kind of boring events, like going through a hallway, or this is actually going through a hallway blindfolded. I don't know if you can see the little black blindfold. Again, this is all made by those two students, Matthew and Eitan, from scratch, which is pretty cool. Here the robot's trying to identify a face among 3 objects, only one of which is a face. And I'm going to mouse over, like, here's another event where the robot has to follow a red line, or listen to this speaker up here. So each of these events takes one or more perceptual capabilities. So like the robot being able to see a colorful line or listen to a sound. Here it's like understanding English. That says turn left. Turn left is what that says right there. So like understanding spoken commands, being able to identify faces. This last one is just a gimme, and that's why it's worth only 2 points. So you play this game where you're trying to kind of guess what the robot is able to do. So let's say I like pick room A, right? A bunch of other stuff happens. They ask you to do a survey. And then you actually get to see, as if you were there with the robot, you get to see a video of the robot trying it. I'm going to turn off sound. So here the robot is blindfolded by a sweatband that we found in the lab and is driving through this hallway without running into any of the walls. It gets kind of close. It's actually doing this all by itself with some code that Matthew and Eitan wrote. And then it goes into the second event where there's a picture of a face and it goes towards the picture of the face successfully. And then it makes a little happy sound. Doo-doo. I'll play that one more time. So even though you're not there with the real robot, you get to see these real videos of the robot behaving. And so you get these, from a kind of psychology point of view, you're getting these real stimuli where you're seeing all the details of exactly how the robot moves and kind of the sound it makes when it moves and the way it reacts to all the different stuff in the room. So there's a lot for you to be kind of drawing conclusions off of, like, okay, so like what was it really able to see as it went through the hallway? It was blindfolded, but it didn't run into any walls, but it kind of got close. What was going on there? And really, we're trying to get inside people's heads here and understand how they react to these different videos. Then the robot makes a choice. And this is kind of the second part of our research, which is like, how can the robot make choices that kind of teach the human what the robot can and can't do? So the robot has seen that I chose room A, and that room A has certain skills. And the robot says, oh, okay, so maybe he thinks that I can do those things. then the robot has chosen room C. And room C, actually, the robot is not able to do. The robot is not able, in this scenario, to understand this turn left command. I'm not sure if you can hear this sound, but it says turn left. Turn left. And the robot just kind of gets stuck there. And it goes, boo, it makes a sad sound. Okay, so the robot fails at a room that it chose on purpose, okay? So, like, people hopefully are going to put together, like, okay, it said turn left, you know, the little map said turn left, you know, the robot drove up, it said turn left, and then it didn't turn left, and it failed, and I got 0 points. Okay, so the robot, like, couldn't do that. And then we don't know what kind of conclusions people are going to draw. Like, did it not hear the turn left at all? Did it hear turn left, but it didn't, like, it ignored it, or it didn't interpret it correctly, or like it just like had a fluke or a malfunction of some sort? Like, it was just like some sort of random thing. What happened? And people are going to draw some conclusions. And then it's your turn again. Oops, sorry, that's the replay. Submit and continue. So then it's your turn again, and there's another slew of rooms here. Yeah, so the goal of playing this game and collecting these data is to develop a way for the robot to build a model of how people react to these different rooms and come up with the best way to choose its own rooms to teach people over time. And I can kind of show you, now I'll just stay here and explain it. We designed the game board in kind of a tricky way. So you just see each room and you're like, okay, I need to like choose, you know, try to get the most points here, try to choose something that Denise can actually do based on what I know so far. But actually there's like a special structure to the rooms. There's 5 floors, and on the 3rd and 5th floors, there's a room that looks really tempting, that's worth like 50 points or something, way more than the other rooms, but it's something that Denise can't do. And so that motivates Denise to like prepare you for that floor and like teach you before you make that mistake that Denise can't do that and that you need to choose something else. Otherwise you won't get the max score for the whole game. So this is just kind of a way to put everything into points and numbers so that like an algorithm, like we use kind of a straightforward like decision-making AI algorithm, so that algorithm will be able to tackle this game pretty easily. So we kind of put it into those numerical terms. But yeah, so we structured the game board so that Denise must learn to teach you stuff. And in order to learn to teach you stuff, Denise must have an idea of how your beliefs change based on what Denise does. Denise has to know that, like, if I show you room number 3 on floor number 2, you're going to learn that I can't understand the turn left thing or whatever. So in fact, we've seen that we've been able to get Denise to intentionally fail at some rooms early on that are worth not very many points in order to save more points later on by preventing a mistake that the human could make. So why does this matter? This is kind of a toy game that we made up that, you know, it's very abstract. It doesn't really look like real life. We kind of rigged it, right? We made it so that there's like a special scenario on floor 3 and floor 5 where you're going to fail if you don't do the right thing. But this is kind of a picture of a like a simplified picture of a lot of real world scenarios where, let's say you're working together with a robot on a factory floor and you've just started working with it, or you're using it to do something that it's just beginning to be able to do. It just got a software update, something like that. The robot could potentially use software like this to do its actions in such a way as to help you understand what its new abilities are and what's changed about its abilities. And it could actually use something about human psychology to do that in an intelligent way. And it would smooth the interaction between you. It knows that you don't know about its software update yet. And so it'll do some things to kind of say, oh, look, I can do this differently than I could before. Or it won't do the old thing anymore. Or it might even show itself not being able to do that anymore and intentionally make a small mistake to prevent a big mistake later. So this is all the sort of intelligent behavior we eventually want robots to have. Yeah, so that's kind of what I wanted to give you all an overview of. I hope it made sense. I'm glad to kind of like go through other parts of the game and continue to show you examples, but I want to get to your questions and we can have kind of a discussion. So let's do that. I think I saw some questions roll in, Ashley. Do I just read them out?
Sure, you can read them out if you can see them.
Well, if I can see them. Oh yeah, here we go. Yeah.
There are 2 questions in one, just so you know.
2 questions, what, sorry?
2 questions in one. Actually, I'll read it to clarify. So this first one I think is also for David. It's, are simulators a one version fits all?
Yeah, thank you for your question. I think this is a really good question. No, simulators. Oh wait, let me show you my face one time. Simulators are not one size fits all, or like a one simulator simulates everything. And part of the reason for this is because systems exist at different scales, right? So in one view of a simulator, we want to have an entire car driving around. In another simulator, we want to really simulate like what are the thermal properties of the brakes as the car brakes, as the car applies the brakes. And so like if every time that we're just driving a car around in a simulator to try to maybe teach a robot how to drive the car, and we always had to simulate what are the thermal properties of the brakes, it's just way too much to do. And so this is sort of why simulation, I think, is an exciting research field, is because there are so many different systems to simulate and so many different ways to use this simulated information. So yeah, thanks again for your question. I think it's a really good question.
Cool. And the second question is, if your research on privacy was based on visual impression or interaction based?
Yeah, I think, so if I understand the question correctly, I think you're asking like, is it based on like when someone just looks at the robot for the first time, and like what is the robot's appearance like? Like, does it have eyes? Is it shiny? Is it cute? And then interaction based, I guess, would maybe be like as you do stuff together with it, or maybe watch its behaviors or something like that.
I believe they were referring to your previous research on privacy.
Yeah.
They were asking.
Okay.
Yeah, like if you want to elaborate more on that other research that you did.
Yeah. Okay. Yeah, and I think it's so again, this research I'm presenting today is kind of the extension of that. This is the closest I think I've done to doing like a visual impression based thing about privacy. Like back when I was in my PhD, me and my advisor had this idea, which we refer to as the googly eyes experiment. And the googly eyes experiment was like, imagine you show someone a new robot and it's just like a cube or something, and it drives around and it vacuums stuff or goes and gets you a cookie or something like that. And then imagine you have the same robot next to it, except it has some big googly eyes on it. They're like plastic and they obviously don't do anything, but they look like big old eyes. How do the googly eyes maybe change the way people like view the robot? Does that make people more likely to feel like they're being watched, or maybe even like make them question like, oh, what if maybe the robot has like a hidden camera somewhere or something like that? Like how does it kind of nudge someone's mind a little differently, even though they're just like obviously big old fake googly eyes? So this experiment here is actually like a little bit inspired by that. Back in my PhD work, the privacy stuff, I had several different experiments, and they weren't as related to this mental model stuff, except for the very last one, which was actually a kind of a silly sounding experiment. It involved, we made this really cheap robot out of a shoe rack we got from Home Depot, and we called it the mobile shoe rack. and we deployed it outside of a yoga classroom at our university. This was up at Oregon State University. So it like patrolled the hall outside of this yoga classroom, like soliciting people for their shoes, because they were supposed to take off their shoes before they went into yoga. Otherwise they would get the floor dirty. So we kind of struck a deal with the yoga instructor, who actually ended up being one of our participants, to like let this robot roam the halls. And all it did was just like drive up to people and beep. It would be like beep boop, and just like sit there and wait for, you know, a gift of some shoes. And the point of that experiment was mental model related. It was like, how do people, we didn't explain the robot at all. We're like, the mobile shoe rack will, you know, be there tomorrow. Put your shoes on it if you want. And that's all we said. We didn't tell them like it can see you, or it follows a certain, you know, it will stay within this box, or it drives in a certain way, or we didn't tell them whether someone was remote controlling it or if it was autonomous, like driving itself. We didn't give them any details, but we picked a couple, or we asked for a couple volunteers from the class who we interviewed every week, and asked them like a bunch of in-depth, really carefully worded questions to try to pick at like what they thought the robot could do. So that was the mobile shoe rack experiment. And it was a big experiment. It ran over like, I think it took 6 weeks. We kind of ran it twice, but the second time was the time that I wrote a paper about, and that was about 6 weeks. And we learned all sorts of stuff about how, like what sort of cues people look for, and what sorts of impressions they get about the robot. Like, for example, one kind of crazy result is, even though we had somebody secretly driving the robot the whole time, back and forth, according to some certain rules, no one suspected it. For some reason, like nobody, like, it didn't cross anybody's mind that someone could be remote controlling the robot, which is interesting, right? And kind of scary that like maybe someone could be like watching through the robot's camera, which our remote control driver was, and like no one could even like think that. I guess at least if you design the robot correctly to make nobody think that, which we accidentally did, I guess. So yeah, adventures in the world of human robot interaction research. I don't know if that like kind of answers your question. I'm glad to, if you want to elaborate on it a little bit, I might answer it more specifically, but there's a story for you from days of old. If you don't ask any more questions, I will feel that I have failed. So I request more questions, please.
In the meantime, usually at the end, we ask what made you guys want to do a PhD, or for Matt, a PhD and a postdoc. So if you guys want to answer that. Okay.
Did David already go?
No, he hasn't.
You're right. Matt, do you wanna go first, as you have a PhD and are doing a postdoc, so I think you have more information.
Yeah, so technically you could ask questions like, why did you decide to do a PhD? And then afterward, did you think that that was actually a good idea? Looking back now, I'm kidding. Yeah, I decided to do I didn't think I was going to do grad school when I was in undergrad. I was doing mechanical engineering, and I really liked doing 3D design, like where you draw 3D pictures of different, like you design different parts and use software to do that. I thought that was like the coolest thing ever. I really liked doing that. I learned how to do that on a robotics team in high school. And so like I wanted to get a job doing that. But near the end of my undergrad, I actually kind of don't remember exactly how it happened, but I started feeling interested in grad school. I had friends kind of suggesting it to me. I think partly on the grounds that I was always kind of interested in more like academic things. Like I really liked learning. I liked reading a lot. I liked discussing. Like I was in kind of like discussion groups and book groups, and like talked about philosophy. These are not reasons that like everybody goes to grad school necessarily, but that's some of the reasons why my friends were like, are you sure that you like, do you like school? And I was like, yeah, I really like school. And for some reason, I had never connected in my mind that I had loved the robotics team in high school. It was like the best thing ever. But then what I took out of it was like that I would spend the rest of my life, not the rest of my life, but like that I would enter a career like working on this small part of it, just the like designing 3D parts, which is great. But like for some reason, it had never really clicked in my mind that like I could do robotics, like all of robotics, like take a higher level look at robotics, like as part of my career. And I definitely didn't know that there were grad school programs in robotics or very much there. And I didn't even know human robot interaction existed as a field until I think like either the very end of undergrad or when I started grad school. Yeah, end of undergrad, because I had been interning in one robotics lab that was like, they built robots. But then I also took a class from who would later be my PhD advisor, Bill Smart, and he did this like different thing where they would look at kind of the way the human thought and the way the robot could interact with people. And so I started getting interested in that. And so my interest drifted over those first couple of years of grad school, and I slowly became more interested in psychology. Human robot interaction is a really interdisciplinary, like a place where people from lots of different fields kind of converge on this one topic of how people and automated technology can work together. So I think that's really cool. Yeah, I've talked a lot, so I'll let it go at that. But those are that was kind of a little bit of my journey and how I got interested in it. And then I discovered human robot interaction, which I think is really awesome. So.
Yeah, thanks, Matt. Yeah, I think, let's see, for me, I have always been really interested in robotics. I actually was never on a robotics team in high school or anything like that. But I did a lot of undergraduate research in robotics, and was considering applying to grad school for a PhD because I enjoyed working with robots. And because grad school seemed like a great place to do robotics. But then I got a robotics job in industry, and I went to industry and was able to work on robotics there. And I think that was a really important little deviation for me, was going and working after undergrad. At least for me personally, it really helped cement the reasons that I wanted to do a PhD, which for me were to kind of practice creativity in engineering. So the PhD is really set up to learn how to ask very specific questions. At least the PhD in engineering is how do you ask specific questions. So if I take this to use some really jargony stuff, like if I take a rigid body dynamic simulator and I make it fully differentiable, what does that build for me? Like, what can I do and how can I show that this is better for robotics than not? And so this is my current research project. But being able to learn how to ask these very specific questions in an engineering context and how to be creative as an engineer, there are many ways to do that. But for me, I really liked the setup of the PhD to do that. I think it really formalizes that process where you learn to ask these questions.
Thank you. We have another question. Someone, Echan says, that's really interesting. Thank you so much. If I want to continue to do robotics and have an interest in aerospace, what is the best course of action when in college?
Yeah, I've got a couple things if I could start on that. I don't have a lot of specific experience in aerospace. David, you didn't do any aerospace in college, did you?
I did not.
Yeah, okay. I know there's a lot of great programs that have, I think, been gaining a lot of steam over the last maybe decade or so in aerospace. So there's great options there. But just like some quick comments about how to use your undergraduate time. I think there's a lot of things that happen in undergrad. I mean, obviously you're making friends. You might be kind of gaining some life skills, learning how to be an adult more than you have before. Maybe not if you're coming to college after working for a while or later in life. But one kind of trade-off I think that happens in undergraduate is between like learning useful, marketable skills and exploring kind of the landscape. And it's sort of a trade-off because, you know, if you spend all your time exploring, you never like really put your nose in a book or, you know, into a problem and pick up skills that you could use at a job. But then on the other hand, like if I had just spent my whole time in college, like specializing in 3D modeling, I would never even like have learned that human robot interaction was a thing, right? So I think it's good to do a little bit of both. And in terms of exploring, so in the area, I guess, of aerospace, like obviously like trying out aerospace, taking different sorts of classes within it, exploring neighboring classes in different fields, because I think aerospace probably kind of multidisciplinary. There's going to be some thermal stuff that kind of might sit a little more mechanical engineering, maybe some design stuff. There are subfields in there, and you'll also see where they touch other disciplines outside of aerospace. And getting that sort of breadth and maybe following your nose a little bit, like just doing things just because you're a little bit interested in them, you might discover, like at this point, you might feel like, oh, I have surveyed the landscape and aerospace is what I want. But like, at least from my experience, like you have never fully surveyed the landscape. Like there's so much stuff out there that you've probably never even heard of. So taking that kind of viewpoint, like that you might not have actually found some important things that might be interesting for you, and like keeping your eyes open can be really good. But I also don't want to advise you to like drift around the whole time. If there's stuff that you kind of lock onto, like, oh, this class is awesome, or like working with this professor is awesome, doing some undergraduate research, which I definitely recommend, then, you know, sink some time into that and develop that. And going deeper is also a way to sometimes discover neighboring things. I guess that kind of contradicts what I said a moment ago, but sometimes, you know, if you sit in a lab for a while and really build some relationships and you're working on a project, you might bump into someone who's doing something you've never heard of and also learn about it that way. So those are a couple comments. And David already touched on like getting an industry experience, doing an internship, which I think is really important. I always would advise people to like do at least one internship and have at least one research experience, which could be, I guess, industry or like a lot of times there'll be academic research available at your university. So I definitely recommend doing at least one of each. So that way you can kind of decide when you get out of college, like, do I want to go on to grad school or do I want to go into industry or something in between? There's lots of different options.
Yeah, I don't know if we're both answering these questions, but I think Matt brought up the most important point for me, which is to do the thing that you're most interested in. So I currently work in robotics, and like have, I think, been able to do almost everything that I wanted to do from like a career point of view, in terms of working on teams that I've wanted to work on or being funded by funding sources that I've wanted to work on. And in undergrad, I studied math because I thought it was the most interesting topic that was out there. So I think I wouldn't worry too much about having a laser like focus. Like don't try to plan from the end of your, like, don't try to plan from the end of college backwards. Like definitely try to plan from like the beginning of college forwards, where you take something and you find it really interesting, and then you continue searching for things that you find interesting. I think that this is really, it's not really feel-good advice. I think that this is really the way to hone in on something that you will really succeed at, and that you will be the happiest doing, and that you will actually have energy to pursue. So yeah.